Throughout the nation, the current mainstream methods of food production create a significant amount of greenhouse emissions, deforestation, and waste. A solution may reside with hydroponics. Here, at the University of Utah, a team of 8 engineers explored this agricultural method by developing a subtype of hydroponics called aeroponics. Viewing the system from the front, an overview shows the major components for an aeroponics system. The totes, which act as a root chamber for the housing of the plant roots. A controls box operates the autonomous functions of the system. Artificial lighting shines down onto the plants. Filtered water reservoirs stand by to refresh the water in the system. And a dome container on top of a heated mat that acts as a nursery for seedlings and new growth. Each plant starts inside a rock-wool cube, which rests inside a net cup held in place by a neoprene disc, and full-spectrum LED lights simulate real sunlight, last longer, and require less power. Inside, the closed chamber minimizes the amount of water lost to evaporation. In aeroponics, the roots of the plant are suspended mid-air inside the closed chamber. An ultrasonic fogger vibrates a ceramic disc at high frequencies to reduce the nutrient and oxygen-rich water to a particle size less than 5 micrometers. Each atomizer rests inside a net cup, surrounded by a flotation disc to maintain near optimal atomization height. Designed to only run at night for reduced noise disruption, a submersible pump agitates the water with a turbulent flow to circulate the dissolved nutrients. An air pump diffuses oxygen into the water to ensure the chambers maintain high oxygen levels and help deter root rot from developing once the plant's roots reach the water. Within the controls box, the system utilizes various electrical components, an Arduino Mega, various sensors, an ESP01 Wi-Fi module, and power relays. The Arduino Mega microcontroller acts as the brain of the system by collecting data from sensors, controlling the relay board, and communicating information to a user interface application called Blink via a Wi-Fi connection. The sensors utilized by the system are a DHT22, which collects the internal humidity and temperature data but cannot be immersed in water, and a submersible DS18B20 sensor that also collects temperature data from inside the totes. An analog probe monitors the pH of the nutrient water, notifying the user if the pH goes out of balance. The ESP01 Wi-Fi module connects the microcontroller to the internet by using Blink, an open-source LOTE application. Through Blink, users have the option to build a graphical user interface that allows remote control of their system for calibrating sensors, performing maintenance, or monitoring the system as a whole. A relay board controls 8 individually addressable outlets powered safely through a surge protector. These operate open-loop controls for the atomizers, pump, and airstone cycles, while the lighting runs on a day-night cycle. All operations utilize Blink's time and date functions to iterate on time without fail. By turning off the timers through Blink, users can disable the system to perform manual maintenance such as planting new seedlings, refreshing the water supply, and harvesting plants. The Blink app keeps track of and displays the plant's growth cycle, and detachable piping reduces the amount of time spent resetting the system. Regrettably, we are out of time for this project, but the research for a sustainable future using hydroponics will continue. Although food production using fog-based aeroponics lacked research, this project managed to explore this hydroponic method with an engineering approach. Understanding the needs of DIY aeroponics also assisted in the creation of quantifiable metrics for a successful prototype. Despite COVID-19 derailing the team's plans, the original goals for the system were still met. Thank you for your time, and we hope you get hooked on ponics.